Good day, good evening, whenever you're watching this. Today we're going to look at lesson 4.2. So in 4.1, we introduced discrete random variables and how to find their probabilities, how to display their probabilities. In this lesson, we're going to find what's called the expected value. And it's, in a way, finding the weighted average, which we did back in chapter 3. Okay, so I'm sorry, back in chapter 2. So we're going to add on to that kind of weighted average and also learn how to find the standard deviation. And I'm going to take you back in the assignment back to I think it's lesson 2.7, where we had a frequency table and it asked you to find the standard deviation, and I gave you the raw data. But now I'm going to have you kind of go back and look at that problem and see if you can look at it in the light of what they were asking. So let me show you my paper here. So we're at 4.2. It says the expected value is often referred to as the long-term average or mean. This means that over the long term of doing an experiment over and over, you would expect this average. So if you think back into chapter 3, where we were doing experiments or probability, rolling the dice, drawing cards. So they're kind of talking about if we were to go to Vegas, we might walk up to the roulette table and put some money down on 34 red. And let's say the first time we play, it comes up. So we automatically think, whoa, we're winning, we're going to play again, right? But the expected value is if I were to continue to put my money on 34 red and keep playing over and over and over again, I would not expect to win every time, right? There's an expected value that I might win or average my amount over time of playing the game over and over. Okay, so let's look at a couple of examples. A men's soccer team plays soccer 0, 1, or 2 days a week. The probability that they play 0 days is 0.2. The probability that they play 1 day is 0.5. And the probability that they play 2 days is 0.3. Find the long-term average or expected value, mean. Remember, we do the population mean as mu. Expected value will always use the symbol mu because we're assuming it's always population value. So find the long-term average of the number of days per week the men's soccer team plays soccer. To do the problem, first let the random variable x be the number of days the men's team plays that week. X takes on the values of 0, 1, or 2. Construct a PDF table, adding a column of x times p of x in this column. You will multiply each x value by its probability. So 0, 1, and 2 days. So remember, this is the days that they play soccer, and the probabilities are here, which they gave us. And so we said we had 0 of those probabilities. We've got 0. We had 1 of the 50 percenters, 1 day of the 50 percenters, so that's 0.5, and 2 of the 0.3s, we have 0.6. Now, our instructions say to add the last column, x times p of x, to find the long-term average or expected value. So when we do that, we get 1.1. The expected value is 1.1. The men's soccer team would, on the average, expect to play soccer 1.1 days per week. The number 1.1 is the long-term average or expected value if the men's soccer team plays soccer week after week after week. So we say mu is 1.1. Now we know that they can't play 0.1 of a game. We know that, but we're talking about just the overall long-term average. Let's go back to the example that we looked at in 4.1 regarding the number of times a newborn baby wakes its mother after midnight. Now, we had already made this much of the table back in 4.1. So we said the babies that they had sampled, there were 50 of them. That's why our denominator is 50. And they woke up their mother after midnight 0 times all the way through 5 times per week. So here were the probabilities that we came up with. So we're going to first find the expected mean. So we have to find x times p of x here in this column. So you would be creating this column on your own. So when we do that, we get 0, 11 over 50, 46 over 50, because when you multiply a number times a fraction, it's the number times the numerator, because this is like an over 1 fraction, if we envision that. So 4 times 4 is 16, 5 times 1 is 5, 3 times 9 is 27. And if you were to add these fractions, you would get 50 over, you would get 105 over 50 down here. So it says add the values in the third column of the table to find the expected value of x. So the expected number of times that a baby would wake its mother after midnight is 2.1. We're going to learn how to find the standard deviation. So it says use mu to complete the table. The fourth column, right here, this is the fourth column up here. We're going to be creating this. Of this table will provide the values you need to calculate the standard deviation. For each value, x, multiply the square of its deviation by its probability. So we did these deviations right here back in chapter 2. So 0, the outcome of 0 times that the baby woke its mom after midnight, minus the mean that we just calculated, 2.1. We're going to square that deviation. That's why it's squared. And we're going to multiply it by its probability of happening. Okay, the number of times out of 50, which is 2 out of 50 or 0.04. And so we get 0.1764. Then the likelihood, let's say down here, of a baby waking its mom 3 times after midnight, that would be that 3 times minus the average of 2.1, square that difference, multiplied by the likelihood of its waking its mother, which is 9 out of 50 times, or 0.18. So that product becomes 0.158. So after we do that with each outcome, it says add the values in the fourth column, which we did, and we get 1.05. But remember, standard deviation is the square root. So the standard deviation of x is the square root of this sum. So this is really the variance, which we will not use, but the square root is right here. The square root of 1.05 is 1.0247 is the standard deviation. Okay. So on average, we would expect a baby to wake its mother 2.1 times. And then we're going to add in the standard deviation. Remember, we did this back in chapter 2, but we're going to add in this give or take 1.0247 times after midnight. So the difference is back in chapter 2, instead of multiplying by the probability, we would just be multiplying by the frequency here. Okay, so instead of multiplying by the frequency, we would multiply by the frequency, and then at the end divide by the total number of observations, because that's essentially what they did, was they divided by 50 on each of these. We'll go back and look at one later. Okay, let's try one on our own. So it says, a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. So we're going to multiply here. 0 times 4 over 50 is 0 over 50, or 0. And then 1 times 8 over 50 is 8 over 50, or 0.16. 2 times 16 over 50 is 32 over 50, or 0.64. Three times times 14 over 50 is 0.4, whoops, 42 over 50, which is 0.84, no, 52, 12, no, 42. 4 times 6 over 50 is 24 over 50, which is 0.48. And 5 times 2 over 50 is 10 over 50 is 0.2. So the expected value, the mean, is going to be found by adding 0 plus 0.16 plus 0.64 plus 0.84 plus 0.48 plus 0.2. Point as is. We get 2.32. On average, we would expect the post-op patient to ring for the nurse 2.32 times in a 12-hour shift. Okay. Let's look at gambling. I'm not advocating for gambling. I like to go to the casino because it's just something fun to do, but always make sure if you gamble, you should gamble responsibly. So suppose you play a game of chance in which 5 numbers are chosen from 0, 1, 2, 3. There should be a 4 here. 4, 5, 6, 7, 8, and 9. A computer randomly selects 5 numbers from 0 to 9 with replacement. You pay $2 to play and you could profit $100,000 if you match all 5 numbers in order. You get your $2 back plus the $100,000. So your profit, which is what you make over what you spent, is $100,000. Over the long term, what is your expected profit of playing the game? To do this, set up an expected value table for the amount of money you can profit. Let X be the amount of money you profit. The values of X are not 0, 1, 2, 3, 9. They are the amounts that you could profit. So the values are, you could profit $100,000 or -2. You'll see that down here in the table. When I make my tables here for these expected values, I usually will write in words what the outcomes are. So like loss and profit or loss and win. And then the X value is how much they would lose or win. So they would, if they lose the game, they lose their $2. So make sure that that's a negative. Make sure that you remember that that's a -2. If they win, they profit the $100,000. Then in your P of X column, you're going to write the probability of losing and the probability of winning. So up here, to win, you must get all 5 numbers correct in order. The probability of choosing one correct number is 1 out of 10. So because there are 10 numbers, you may choose a number more than once. The probability of choosing all 5 numbers correctly are in order. Now remember, they're all 1 in 10 because they are independent. We replace the number back in. So it's 1/10, 1/10, 1/10, 1/10, 1/10, or 1/10 to the 5th, which is here. So this is your probability of winning the $100,000. Not likely. Therefore, the probability of winning is this, and the probability of losing is 1 minus that because they're complements. They have to add to 1. Okay. So to do a profit, we would multiply our X times our P of X here. So we get a -1.99998 and we'd multiply our x times our p of x here, and we would get 1. So it says since a negative point, so if you were to add these, you get this right here, which is very close to a negative 1. So you would, on average, expect to lose approximately $1 for each game you play. However, each time you play, you either lose $2 or you profit 100,000. The dollar is the average expected loss per game after playing this game over and over. So more than likely, you're going to lose $2, $2, $2, $2, $2. Once in a very blue moon, you might win the 100,000. So on average, your expected loss is the dollar. Let's do one of these on our own. So suppose you play a game with a spinner. You play each game by spinning the spinner once. The probability of red is 2/5. The probability of blue is 2/5, and the probability of green is 1/5. If you land on red, you pay $10. Yikes. If you land on blue, you don't pay or win anything. If you land on green, you win $10. Complete the following expected value table. So red, they said if we win on red, you pay 10. So it's a negative to us. And if you win on blue, you don't pay or win anything. So that's a 0. And we profit 10 if we land on green. The probability of landing on red, they said was 2/5. We already have the probability of blue, and the probability of green is 1/5. Always make sure that these total to be 1 or 5 out of 5 in your probabilities to make sure you're correct. So my x times my p of x would be a negative 10 times 2/5, which is a negative 20 over 5. Then we have 0 times 2/5, which is 0 over 5, which is 0. This comes out to be a negative 4. And then 10 times 1/5 is 10 over 5, which is 2. So our expected value or loss would be a negative 4 plus 0 plus 2, which is a loss of $2. I'm expecting, if I keep playing the spinner game over and over and over again, I may win the $10. And if I do, I better leave, right? Because the next time I spin the spinner, I'm probably going to either win nothing or lose $10. So over and over and over, on average, we would expect to lose $2. Okay. So on May 11th, 2013, at 9:30 p.m., the probability that moderate seismic activity, one moderate earthquake, would occur in the next 48 hours in Iran was about 21.42%. Suppose you make a bet that a moderate earthquake will occur in Iran during this period. If you win the bet, you win $50. If you lose the bet, you pay 20. Let X be the amount of profit from a bet. So you can see in our table that we made, we have a win and a loss, or the outcomes in words, and the win would be a profit of 50. If you lose, you pay 20. The probability of winning is the probability that you have an earthquake occur, because that's what we're betting. So 0.2142 in decimal form. The probability of losing is going to be 1 minus that, 100% minus that, which is 0.7858. So remember that these two right down here in the probability of X have to add to make 1. Now, if we take X times P of X, I'm going to show you how I calculate this. So 50 times 0.2142, we get the 10.71. And then a negative 20 times 0.7858, we get the negative 15.716. So if we add those together, we get an average of negative 5.06. This is our expected value right here. So we're going to go through and calculate our standard deviation. So we have to take our outcome X, 50, and subtract the expected value. So we're subtracting a negative, remember that. And then that right here, that sum or subtraction will get squared and multiplied by the P of X of 0.2142. And then we're going to do the other expected, the other outcome, which is a negative 20. excuse me, you're going to pay $20. And then when you add that to the 5.06 and square it, you multiply by the probability and you get this. So we add those products together and take the square root, and our standard deviation is 28.716. So our standard deviation is very, very large compared to our expected value. And that's because it's the probabilities are so far different from each other. The likelihood of winning is so small compared to the likelihood of loss. So let's do one of these on it together here. On May 11th, 2013 at 9:30, the probability that moderate seismic activity would occur in the next 48 hours in Japan was about 1.08%. So not as likely as in Iran. As an example 4, you bet that a moderate earthquake will occur in Japan during this period. If you win the bet, you win $100 because it's a lot less likely than the one in Iran. If you lose the bet, you pay 10. Let X be the amount of profit from a bet. Find the mean and standard deviation of X. So our outcomes are going to be loss and profit. So our loss is $10 if we lose, and our profit is $100 if we win. And if we, let's go by if we win, because if they have the earthquake, that would be the profits. That's going to be 0.0108. Make sure that you calculate those correctly. So 1.08 divided by 100 to move the decimal, so 0.0108. And 1 minus that 0.0108 is the probability of us losing. Very likely that we're going to lose. The likelihood of an earthquake in Japan is not really, at that time, was not very likely. There's definitely different times of year where they're more likely. So we're going to multiply a negative 10 times 0.9892, and we get a negative 9.892, and then 100 times 0.0108. So if you don't have a calculator, a physical calculator, I would use Desmos for these calculations. Using your cell phone, at least for me, I accidentally kind of touch in the wrong spot. So I really encourage you to either have some kind of a handheld calculator that is easy and convenient to use, or Desmos. So we have to find our mean, the expected loss or profit. So we're going to take a negative 9.892 and add that to 1.08. And we get a negative 8.812. So we have to do here X, which is a negative 10, subtracting, remember subtracting, a negative 8.12. We have to make sure we subtract that. Then that gets squared, and then we're going to multiply that by the 0.9892. Now put that calculation down here. So we are going to, in parentheses, we have a negative 10 subtracting a negative 8.812. And then I'm going to square that. And multiply with 0.9892. So we get 1.396. Now, if you have a graphing calculator, the handy dandy part about this is I can just arrow up and highlight it. See, I'm highlighting and hit enter and it copies it, and then I can just go and edit. So this was, I profit 100, subtracting the negative 8.812. And then I'm going to enter and then multiply that by 0.0108. That's 127.87. So my standard deviation is going to be the square root of 1.396 plus 127.87. Okay, so the square root of 1.396 plus 127.87 is 11.37, rounded to 2 decimals is fine. So there is my mean and my standard deviation. So let's go back to the question from the book. Maybe just 1 minute. I'd like to look at that back from chapter 2. Okay, I wanted to take you back to the problem from the book on page 157. If we go to our book for a moment, and page 157, it's asking you, they give you a table here. Okay, right here it is. So it says 40 randomly selected students were asked the number of pairs of sneakers they owned. And they owned anywhere from 1 pair to 7 pairs, and here was the frequency. Then I gave you just the data set where I taped out all of those individual people. Let's see, there were 2, 5, 7, 15, 27, 39, 40 students. Okay, so I typed out all of those. And so in your homework, you should have just done the mean of x1 and got 4.56. And then you should have gotten the standard deviation of x1, and you would have gotten 4.849. Okay, now if we go to decimals, I have created this in the table form like it was on page 201 in the book. Okay, and so I'm going to show you how to use the expected value method of finding the standard deviation when it's in a table form and there's frequencies instead of all of the original data. So just like we did in the exercises just now, we multiplied x1 times y1. Okay, so x1 times y1 is here in this purple column. Okay, so we're going to find the expected value. So I'm going to make it on here. Expected. So we're going to sum. We're going to total. It's summing, but we're going to total x1 times y1. And that's our expected value, which is 151. Okay, now I'm going to go up here and I'm going to make a new column. And this column, I'm going to take and I'm going to multiply my frequencies, which is my y1, I'm going to multiply those by my observation of x1 minus 151, my mean, and I'm going to square those. Okay, so these are all of my this is my column here. So I'm going to total that column. I'm going to add those up. So y1, and it was star, parentheses, x1 minus my mean squared. Okay, and then I have to take the square root of that. 867,073. Oh, I know. I have to divide by 40. Weird. Is there a 40? Let me back up a bit. I just noticed I had an error in my data. I don't know if any students caught that, but I was missing a 3. So I just resaved that and I will reshare that link correctly. And that link will be correct in Canvas. So my mean is actually 3.775 and my standard deviation is 1.2907. If I do standard deviation P of X1, it might even get us closer, 1.2745. I think that's what they're going to use here. Yes. Okay. So when I corrected my data, this is with the raw data. Now, if we go to my table, I calculated my weighted mean incorrectly. I had to do my total, just like we did back in chapter 2, my total of my X column and my frequency column. So my X1 times Y1 divided by my total of all my frequencies. So that's right here. So my expected value is 3.775, just like we calculated with the raw data. Then I'm going to make my totals. Remember, I have to take my frequency times my observation subtracting my mean. And I corrected my mean at 3.775. And I'm going to square those differences, the deviations, and multiply by the frequency. And then I'm going to divide that by the n, or the n minus 1. So we could do the square root of 64.975 divided by n minus 1. So I could do 39. So that would give me the sample standard deviation. And this up here would be the population standard deviation. So this would be the population standard deviation below. And then the n minus 1 is right here. So check those out. So that should help clear up what you were asked to do back in chapter 2. It should help make that a little bit more sense. Catch me back for the last lesson of chapter 4, 4.3.